This is AP, David. This is AP. Hi, Isaac. Again. AP Chemistry. We do an exam review. I updated the stream title. I was just late to updating it. I just ignore them for the most part. I don't know what I'm going to be doing, David. I might... Kind of just depends on if people are interested in what people are interested in, because technically at the end of next week I'm done teaching stuff, so I might just stream like random stuff that I think is cool. But yeah, Bryce, they're just like really off topic, so yeah, I don't know what I'll do. I don't know if I'll yeah, well, I'll figure something out. I'll do something next month. Yeah, I still need to stream Satisfactory, but I've reached a point in the game where I don't really have anything to do, so maybe I can just stream like and do a little factory tour or something. I don't know how many people would watch that. Like, when should I stream that, Zach? When would you watch it? Because I know Zach was slightly interested in it. Who else was interested? Max was interested in it. So, I don't know. That's a fun game. Also, I think my trying to stream that was kind of weird. I'll have to figure that out. Oh, different Zach, David, different Zach. There's too many Zachs. Zach's such a common name. We got it from, see, but then I'd have to buy it, Isabel. I could just stream like the random games I'm playing in my free time. I'll probably stream Clash this weekend for League of Legends because we're planning on playing Clash again. We got our sushi from Sapa Sushi. It's downtown. I think you'd pull up our tier too much probably, David, but I don't know. I think we have our full team of 5 that we play with. We might need a 5th on Sunday, but I don't know what you're up to. Oh yeah, that's true. Your birthday, doing your birthday stream. Yeah, maybe I'll stream something this weekend. I'll probably do Clash this weekend, and then maybe I'll start like throwing in random games and stuff. It's a good one, Isaac. I don't know if it's my favorite one. We don't really have favorite because we don't go that often because sushi expensive. But that's a really good one. We really like that one. Me personally, oh, that's a hard question. I really liked FF7. I played FF7 a lot. Smith Sushi is okay. It's not really good, DJ. Are they really, Naya? That's weird. Maybe they just had like extra frozen in the cafeteria and they're just trying to get rid of it. Yeah, it's really not, but I mean, it's not terrible. Tsunami's good. Ito's good. No, it's not. It's not. Yeah, in terms of quality, it's our bottom quality. Um, yeah. Okay. Let's get started. So I wanted to do some more free response practice. I've got a bunch more free response questions we can go through. Um, and then this is kind of like, so this guideline, all right, this is everything. So I have 3 exams that pull from so these are alternate exams to the ones that I let you guys work through. So these are different questions, things you've never seen. And so I just kind of want to know like what topics you guys wanted to go through. So if you take a chance, you could just look over real quick at these topics that I've identified, and then we can go over whatever. So Isaacs wants to do one of the thermo ones, like the MCAT style thermo ones, or like the delta G. Well, we can't do the delta G, but like we'll do this MCAT one. This MCAT one's good. Maybe we'll start with that. There's a bunch of rates ones, Bryce. We'll definitely hit some rates ones. Let's start with this MCAT one, and then I'll check that other thermochem one here in a second. I can't remember if there's any other thermo ones. I think just this one. We'll do this one. We'll do this one because it's kind of like a one-off, and then we'll maybe do some rates ones. So 2016 question 1. 2016 question 1. All right. So here is our 2016 question 1. What? Oh, David. So 2016 question 1 says calcium oxide has been proposed as a substitute. Student wants to design a heating pad, right, that can heat a 150 gram sample of water from 25 to 60. Okay, so right there, your brain should say, oh, wait a minute, we've got a changing temperature. That's the only thing we really know with changing temperature is our MCAT. I mean, yeah, sometimes gas laws, but it would have mentioned something with a gas. So we've got water and a changing temperature. So then MCAT is where your brain should first go. And then the question says, calculate the amount of heat in joules, for sure, Q equals MC delta T, that the water must absorb for the temperature change by this amount. Assume the specific heat capacity of the water is 4.18 joules. So, right, so we see that's kind of our giveaway of, hey, we need to do a Q equals MC delta T calculation. All right. So from the problem, we're calculating heat. The problem told us we were doing a 150 gram sample of water. They told us to assume 4.18 joules per gram degree C. And then we're going from final temperature 60 minus initial temperature 25, and technically those have point O's on them with 3 sig figs. Okay. Thanks, equation, for the follow. Hey, that works. All right, so the math here is straightforward. It's just plug in and calculate. So recognizing what equation to use, Q equals MC delta T, is a pretty good giveaway. If they tell you, they give you C in the problem. So again, this should be obvious that this is what you're doing here. So 60 minus 25 times 4.18 times 150. We get basically 21,900 joules. And so the problem, oftentimes on these ones, since sometimes they're in joules and sometimes they're in kilojoules, the problem will specify the unit for you. Thanks from Chafuku. Yeah, so I was going to do that probably on Wednesday, Maggie. I kind of need to go through some ideas of what and why. So I'm going to go through that on Wednesday. So I'm still kind of formulating what would be a good thing to do. So we'll plan on doing that Wednesday. All right. So 21,900 joules, because the problem does say calculate the amount of heat in joules. Okay. So 3 sig figs, 21,900. And then number 2 says calculate the minimum mass of calcium oxide that the student would need to use in order to cause this temperature change. All right, so this is where we have to use our delta H of reaction, right? So remember, we can use delta H of reactions, and the way we use delta H of reactions, or the delta H of, a phase change, is we do a factor label. All right, so the way we'd set up this factor label, I'll go back to my screen here in a second, I wanted to leave the problem up, is we want to know the minimum mass, so how many grams of calcium oxide are needed to make the heat we found in part 1, right? So we said it was what, 21,900 joules. So we want to know how many grams gives us the 21,900 joules. So I'm going to jump over to my work here. Okay, so how many grams of calcium oxide makes 21,900? Yeah, so that works for any titration, Isaac. That works for any titration. Yeah, you can do that. So how many grams of calcium oxide? 21,900 joules. Okay. They give us the delta H in kilojoules. So my first change is going to be 1,000 joules is 1 kilojoule. Right. And then I'm going to do 63.7 kilojoules in 1 mole. And then that's for the reaction. It's 1 mole in the reaction, so that's fine. So we can just say 1 mole of CaO. If there had been a coefficient on it, we would have had to take that into account. But because there's not a coefficient in the reaction, we don't have to worry about that. We just have to add up calcium oxide. Calcium's 40 grams per mole, oxygen's 16. So this is 56 grams per mole. So, right, so the big takeaways here is that if you have delta H, you do a factor label. If you have like C, the specific heat, you're going to do Q equals MCAT, right? So we've got those those are our big two in terms of producing and releasing heat. Yeah. Let me double check. This is page 48. Let me double check that I got these problems right. I think I did, but let's double check. Answer keys all the way down here. Question number 1. Oh, oops. There it is. Question number 1A. Yep, 21,000 joules. 19.3 grams. Isaac, I'm trying to think if I have one that does that. Because then this problem dives into like delta G and delta S stuff, which is not going to be on this year's exam. I'm trying to think if there is one that did that. Maybe 2. Oh. No, this one's just delta G. I don't think I have one. Oh, this one, calorimetry. Maybe 2018 question 6. We could, yeah, we could. Let's see, 2018 question 6. Calculate the amount of heat, calculate the number of moles, using the balance of chemical equation. This one's kind of like that. It's more of this calculation stuff. This is a good problem if we want to do some more thermochem. Because I'm trying to think. I don't think question 1. Because yeah, it goes into delta H and delta G, and then it kind of does a little jaunt into KSP. So we can come back to this one. Let's do another thermochem one here. Let's do this one. So let me put like an X on the ones we've done. Okay. All right, so we did that one. All right, so let's look at this problem. So this problem says students asked to determine what mass of butane needs to burn in order to raise the temperature of a 1,650 gram of beaker of sand by 180 degrees Celsius. So here we're not heating up water like we usually do. We're heating up sand. So it says calculate the amount of heat energy needed to raise the temperature of the beaker of sand by 180 degrees. Assume that all the heat energy from the burners transfer to the beaker of sand and that the specific heat capacity of the beaker and the sand together is 0.810. All right. So again, they give you specific heat. So if they're ever going to ask you to use Q equals MC delta T, they're going to give you specific heat in the problem. If they give you specific heat, you should just automatically rote memory Q equals MC delta T. Write it down, try to plug in and see and solve, right? So that's what I'm going to do. I'm going to write down Q equals MC delta T. Q equals MC delta T. They're going to give you 3 out of those 4 variables, right? So let's see what information we have. We're raising the temperature of the beaker and the sand by 180. So that is our change in temperature, 180 degrees. They gave us specific heat as 0.810 joules per grand degree C. Oh, that's terrible. Oh well. And then they told us the mass, but sometimes they get a little annoying with these pictures, because sometimes the information you need to solve this question down here is up here, right? So make sure that you don't get like tunnel visioned on the text here, because this might not be enough information. Often, I've seen this happens actually a lot of the time. You have to go back up to the prompt of the question, the original prompt, to find the number you might need. Okay, so that's kind of some good advice. So they love throwing pictures and diagrams and images. You might have to jump up above that to find information you need to solve the problem. So in our case here, we have this 1,650 grams. Do you have any Hive QL? I don't know any Hive QL. Sorry, man. What is Hive QL? Oh, I don't do a ton with computer science. Sorry, man. I'm mostly just chemistry. I know a little bit of programming, but not enough to probably help you. All right, let's go back. So we've got the math written down. Let me do it. Yeah, if it was chemistry, I'd for sure be able to help you on that. Coding is something I've been always interested in. I did a bunch of it for my master's, but it was a really specific language. Yeah. All right, so I get 240,000 joules. No, I blocked it, David. Blocked it. All right, so 240,000 joules. That's a lot of joules. The problem didn't actually specify the units. So we could either do joules or kilojoules. The answer key probably has both. So 240,000 joules or kilojoules. Yeah, Lauren, so you would be fine on doing both. Be careful though, right? Make sure that you put... Oh, what language did I do, David? Give me a second. Let me answer this question first. So you have to be careful, Lauren. You have to put the unit, right? So you can either say 240,000 joules or 240 kilojoules, but if you just say 240,000 without a unit, they're probably not going to give you points, right? Or if you said 240,000 kilojoules, you're going to get it wrong. So make sure on these heat style problems that you have the math and the unit line up. Yeah. So for my master's, David, I did some stuff in Perl, and I did some stuff in like Linux bash script stuff. So just like some Linux home base programming. The one program I wrote was really in Perl. So I did a decent amount in Perl. Okay. Then we go to our next guy here. Student runs the experiment, collects the data, lots of data. Calculate the number of moles of butane that was used in the experiment. So let's look at the math here, right? Student runs the experiment. We know the mass of the beaker and the sand. We know the mass of the burner before combustion. We know the mass of the burner after the combustion. We know the initial temperature, and we know the final temperature. So this problem is pretty simple. It just says calculate the number of moles of butane used. So we take the before minus the after. and then just convert it to moles. So we'd have to add up the weight of butane, convert to moles. I'm not going to go through that, right? Then part C says use the balanced equation for the combustion of butane. So they've given us our combustion equation and the delta H, and determine the amount of heat energy produced by the combustion in the experiment. So what we can do here is we can calculate. Yeah, I got it in December, David. Yeah, I finished up my degree in December. Let me show you that on the grading key, Isabel. They might actually specify on the grading key, if I remember. So let's see. I'm on page 68. Grading key's near the bottom. Let's see. It was for this problem. So here's our problem, right? So they say 241,000 joules or 240 kilojoules. It says 1 point is earned for the correct calculation of energy. So this one didn't actually specify units, but I assume if you put the wrong units, they probably wouldn't give you this point. On this one, though, it says 1 point is earned for the correct calculation of the number of moles with the correct number of significant figures. Ding, ding, ding. So this is the... Like I've mentioned this to you guys before, usually there's 1 point in the free response that is attached to sig figs. And so this one, you would not have gotten, even if you did the number right, if you just put 0.12, they would have counted off. You would have missed this point for sig figs. So that's why I say to be careful about sig figs on every problem, because you don't know which problem is going to count significant figures, right? I mean, this one does tell you to report it to problem number sig figs. But oftentimes they will count a sig fig problem without telling you that it's a sig fig problem. So when we do this subtraction here, you get the 3 sig figs because it's 2 places past the decimal. And then you do the grams to moles conversion and you end up with 3. So this is kind of cool, just a random sig fig question. So, yeah. All right. What else do we want to do? We want to do some more rates practice. What did we want to do? Let me show you the wheel of problems we have to do. What else do we still want help with? Hello, Sugar Hit. How's it going, man? What else do we want? What do we got? What do you want, chat? KSP, says Isaac. Okay, so I've got a couple KSP problems all throughout. So KSP, KSP, KSP. I think let's do this one. Let's do the 2017 question 6. That's a good one. I like the short problems because the short problems are more like they're one quick topic in and out. The long questions are more like mixed. Those are the ones that we've already done, Naya. I've crossed them out. Yeah, 4x is apparently no good. 3x is okay. No, 3x is definitely no good. Anyway, answer the following question about the solubility of silver chloride. The value of the KSP is that. All right, so they've given us the KSP. Right. So again, I make an emphasis about this because there's so much stuff in the AP chemistry curriculum that if you can zone in and say, okay, what is this problem focusing on? And so there's going to be like keywords and key indicators in the problems. And so they say here the value of KSP. So automatically my brain should go KSP. It just doesn't like you, Naya. So when I say KSP, my brain should think KSP. So we have to remember, what is KSP? KSP is when you have a solid breaking apart into its ions, right? So we have an insoluble solid compound breaking apart into its ions. All right, so it says calculate the value of silver chloride in a saturated solution of silver chloride in distilled water. The concentration of the chloride. Oh, just calculate the value of the silver ions. Can I? Maybe I'll just. I'm trying to think if I want to do. Yeah, let's. I can do this. Let's pull this down just like that. All right. So how would we go about doing this problem? Okay. So the first thing is the concentration of the silver. So in order to find the concentration based on KSP, you would get, you write the equation, right? So we know the equation corresponding to KSP is whenever you have a solid breaking apart into its ions. So we have silver ions and chloride ions, right? So, solid breaking apart of ion. It's very careful to note if we had any subscripts here, that those subscripts would turn into coefficients, right? So, determine just a saturated solution in pure water, we kind of do an ice table, right? Initial, change, equilibrium. Okay, nothing there because it's a solid. So a solid doesn't really affect our ice idea. But we're assuming that we're adding this solid to pure water. So these are zeros to begin with. We know that they're going to gain some amount. We'll call that x. And then we get just x there. Okay. Now our KSP in general is going to be the concentration of the silver ions times the concentration of the chloride ions. Right? And so we know the silver's x, and we know the chloride's x, and we know the KSP from the problem was 1.8 times 10 to the negative 10th. So we just plug in 1.8 times 10 to the negative 10th equals x squared, right? Because x times x squared. So then x is just the square root of 1.8 times 10 to the negative 10th. Or 1.8 times 10 to the negative 10th, right? Really small number. Square root it, and we get 1.34 times 10 to the negative 5th. Yeah, I'm going to do something, David. I don't know what, but I'm going to do something. Yeah, I'm still figuring out what to do. Because I want to keep doing the streaming. I think it's fun, but no, I don't know yet. All right, so this is going to be the concentration of the silver and the concentration of the chloride. Again, I want to reemphasize that if we had a more challenging problem and we had a coefficient of like a 2 here, and so this was plus 2x and this was 2x, that we'd want to take whatever we found as our x and we'd have to multiply it by 2 to get this, some other concentration. So, oh, oops, that's equals. They both equal each other. So to answer the first question, to calculate the value of the concentration of the silver in a saturated solution, it's just 1.34 times 10 to the negative 5th. I don't have anyone signed up to be teacher aides yet, Isaac. If you're interested, you're more than welcome to. You have to. It's like run through the counseling office, though. Hey, not Phantoms. Thanks for the follow. So letter B says the concentration of chloride in seawater is 0.54 molar. Yeah, Bryce, you would. Yeah, if like I said, if there was a 2 here, this problem becomes a whole lot more complicated. I'll see if I can find an example of that after this one. It's good to start with this as a simple. I think one of the other ones might have a 2, so maybe if we've got time, we should be able to do it. So then, all right, this says to calculate the molar solubility of the silver chloride in seawater. So the difference being here is they're telling us that the chloride, the Cl minus, is already 0.54. So because it's already 0.54, we basically just plug that in for the chloride. This had a fancy name. Do you guys remember what this was? Common? I don't know how Isaac has 2 free periods because he's not taking science. Not molar solubility. This whole thing is molar solubility. But when we have this 0.54, hey, there we go. Sarah's got it. Logan's got it. Common ion effect. Logan, you have to change your freaking AP Central email to not be your CS Docs emails. I've gotten like 10 emails from Jan Monker. Change your email linked to your AP account. Oh, okay. Good. Seriously, Jan Monker, so many annoying emails. All right, so this is called... No, I'm just kidding. So this is called the common ion effect, right? This idea, no, you're good, man. I'm just kidding. The idea that once we already have some of one of these ions in solution, it's going to make this silver go down by a lot. And so to solve, we just divide, right? And so our silver is going to be a much smaller value. Whatever that is, 1.8 times 10 to the negative 10th. Divided by 0.54, right? Really small. That's 3.33 times 10 to the negative 10th, right? So you'll notice in pure water, it's 1.34 times 10 to the negative 5th. In the seawater, it's 3.3 times 10 to the negative 10th. So Lauren, that's in the problem. It says the concentration of chloride in seawater is 0.54. And so we just plug 0.54 in for chloride. We can just plug it straight in. So with the common ion effect, because this concentration is so large, it's not going to get shifted because of equilibrium. And so we can just plug it straight into the problem. No, you're good, Lauren. It's a good question. And so again, you'll notice that the silver is much smaller. It's almost like 1,000,000 times smaller because of the presence, the common ion effect, because of the chloride. So explain why the silver chloride is less soluble in seawater than is water. The common ion effect, right? Because of the presence of chloride, that causes this equilibrium to be shifted to the left, right? You can think about it in terms of Le Chatelier's principle. If we have more of this stuff, right, less of the solid is going to break apart. We can check the grading key on it just to make sure we didn't screw anything up. Question 2. Hydration energy's energy of hydration. Let's see. So they have 1.3 times 10 to the negative 5th. Isaac, it's the energy associated when like something bonds with water or when something dissolves is usually the when we talk about hydration energy. And then 3.3 times 10 to the negative 10th, check. And then an increase in chloride would decrease solubility since Ksp is a product. Example of the common ion effect. All right. Let's see if the other ones were more complicated. Let's see. Where was the other? So we did this KSP. Let's look at maybe one of the other KSPs. The problem number 1 here. Oh, yeah. Okay, so this is a good one. All right, so the problem says, student learns that the calcium hydroxide produced from the reaction. Hey, thanks for the follow, Sugarhead. Produced by the reaction. Oops. Wrong way. Is relatively insoluble and it dissolves according to the equation of love. So we have noticed, right? You see this, you see solid dissolving into aqueous and aqueous. And so your brain should say, all right, that's a KSP. Right? A single solid breaking into its ions. Okay, that should ring bells in your head that, oh, this is a KSP. The student prepares a saturated solution of calcium hydroxide and determines that the calcium is 0.011. Calculate the value of KSP for calcium hydroxide. Okay, this is a good problem. This is a relatively complicated problem. So what we want to do is we want to think, all right, calcium hydroxide breaking down into calcium ions. And again, we got to remember this 2 here gives us our 2 hydroxide. Now, they were nice enough to give us that equation, but they didn't have to give us the equation. So what we want to do is we want to set it up just like we're setting up any other ice table, right? KSPs. We'll say, okay, if we have pure water, there's 0, 0, plus x. Now, because we have a 2 here, this means we're going to have plus 2x. Right? That means we've got x and we've got 2x. Okay, and then our K expression, KSP, is the concentration of calcium times the concentration of hydroxide squared, right? Don't forget those coefficients turn into exponents. And then, so if we're going to plug in, then KSP equals x times 2x quantity squared. Now, this is another place that people always make mistakes. They'll forget that that 2 needs to be squared in addition to the x. So both the 2 and the x need to be squared. And so our KSP, it doesn't equal, so we have x and then we have, right, this turns into 4x squared. And so it ends up being 4x cubed, right? So KSP is 4x cubed. Now, this problem didn't give us the KSP, and so we're not going to solve for x because they gave us, they said the calcium is 0.011. Well, calcium is x, and so they're telling us the value of x. No problem. Delaney, Michelle? I went over moles and stoichiometry this morning in my honors class. I don't really know kind of what level you need. So biggest thing is just remember to use the periodic table and your balanced equation. That's kind of the big reference to learn there is how to use your periodic table to change grams to moles, and then how to use a balanced equation to change moles of one into moles of another. All right, so they gave us x here. Whoop. And so we're going to plug that into our equation. So KSP equals 4 times. Yeah, if you want to check out my YouTube channel, Delaney, it's literally my most recent video. Goes through just a real simple overview of stoichiometry. I don't know if that's what you need, but that's kind of what was from this morning. All right, so we'll take 0.011 cubit multiplied by 4. Yeah, there's a link right below the stream to my YouTube channel. Just click on the banner. Okay, so we take 0.011 and we cube it, and then we times it by 4. So I get 5.32, which is 5.3 times 10 to the negative 6th. Oops, and that's unitless because it's a KSP. All right, and then they ask an interesting question. Okay, so questions on how we did this, right? Notice the differences between a 2x and having to square it versus just a plain old x. The rate k has units. So whenever we're talking about a k dealing with rates, Bryce, that's when the units become really important. Our equilibrium k's, KSPs, KAs, KP, KC, those equilibrium k are unitless. But when we're talking about a rate of reaction, that k has really important units. Chapter 1, the mole. Okay, they do ask an interesting question in the part C here. They say the student wishes to significantly increase the molar solubility of calcium hydroxide and has access to the following substances: water, calcium chloride, potassium hydroxide, and hydrochloric acid. Which substance, when added to the calcium hydroxide, would increase the molar solubility most significantly? Justify your choice. All right, so if we think about this reaction and we think about the common ion effect, okay, will water make it more soluble? If we just add more water, is that going to make it more soluble? More of the solid would break apart, but the concentration won't change, right? And so we're talking about concentrations. And so the distilled water doesn't work. The potassium hydroxide is going to make it less soluble because of the common ion effect. The calcium chloride is going to make it less soluble because of the common ion effect. So that only leaves HCl. So how would HCl increase the solubility of calcium hydroxide? What do we know about HCl? HCl is acid, strong acid, hydrochloric acid. What is it going to interact with in my equation? Okay, good. Sarah and Zach both got it. It's going to react with the hydroxide. And if it reacts with the hydroxide, what happens to the concentration of hydroxide? it goes down. And so according to Le Chatelier's principle, if we remove some product, that's going to shift the reaction to the right. And so by removing product and shifting to the right, that's going to increase our solubility of calcium hydroxide. So this is a pretty cool problem. I kind of like the follow-up here. Vapor pressure, Isaac. I don't have time right now, but we could maybe go over it later. All right, so that's that one. Check. What did we say we were going to do? Rates? Was that we had a couple rates questions? All right, let's do the third one from the 2017 exam. All right. So let me move my document camera real fast. All right. Okay, so this is, I'm going to focus in on this part down here. So we're not going to do the whole question. We're just going to focus on this. So it says ozone can oxidize the bisulfite ion, HSO3 minus, right, bisulfite, as represented by the equation above, or below, sorry. Bisulfite reacts with ozone, O3, to make, what is that, bisulfate and oxygen. So we have SO3 turning into SO4, we have O3 turning into O2. Sorry, Micah. A solution, thanks for the follow, Ambitious. A solution is prepared in which the initial concentration of the bisulfite ion, 6.4 times 10 to the negative fourth, is much larger than that of ozone, 1 times 10 to the negative fifth. Concentration of ozone is monitored as reaction proceeds data plotted below. All right, so notice, how do I know this is a rates problem? Right? My first way do I know it's a rates problem is because of this on the bottom, because it says time, right? Whenever you see time, you should think, okay, rate. We're talking about time. Whenever we're talking about time, we're talking about rate. That's the only context that you're going to see time. Right? So notice we have concentration, right? We have concentration and we have time, okay? Now, is this graph of concentration versus time linear? No, it's not linear, right? So what is that? What do we automatically know? We know the reaction is therefore not we know it's not zero order. Careful, Austin, right? Remember, concentration versus time is zero order. Good. So we know the reaction is not zeroth order. Okay, so that's good to think, to get our brains thinking like that. Okay, so we know it's not zero order, right? Let's see what else the prompt says. Let's see what else goes on in the problem. It says the data are consistent with the following rate law. Well, they told us the rate law anyway, but it's still good to be anticipating things like that. So rate is K times O3. So here ozone, right? What order is it based on this rate law? It's first order. Now, how do we know it's first order? How do I know by just looking at this rate law that it's first order? Because the exponent. But there's not an exponent there. There is an exponent. It's raised to the first power. And then, Sarah, yeah, we know that it has a constant half-life. So even if they didn't tell us it was first order, we could potentially have looked at the graph and seen, right? Here's, if we think 1 to 5, that's 1 unit of time. And then 5 to 2.5, that's another unit of time. And then I guess we're saying that's 1.25 is here, so 0.03. Okay, so let's jot down that data on my document camera, right? So we're saying that at time 0, so I'm going to make just a little chart. So time, concentration of ozone. So at time 0, it was... I guess I should move this down a little bit. So at time 0, it's 1.0 times 10 to the negative 5th. Right? And I'm going to jot these half-lives. So I know it's 5 times 10 to the negative 6ths at 0.01 seconds. Right? So this is time in seconds. Right? And then it's 2.5 times 10 to the negative 6th at 0.02 seconds. Right, so this is showing that constant half-life. Half of this, 0.01, half of this, 0.01. So our half-life is 0.01 seconds. So let's look at the problem again. So based on the previous page, determine the half-life. Well, we just did that. T1 half goes 0.01 seconds. Now, we could have also plugged in, but we don't know K. Oh, but now we can determine K. So it says, based on the graph, determine half-life. Okay, so based on the graph, half-life is 0.01 seconds. Determine the value of the rate constant K for the rate law, include the units. So we can use, because we have the half-life, if you ever find or ever use the half-life, you should use this equation, where the half-life is the natural log of 2 over K. Oh, sorry, Lauren. I did that by inspection, is the fancy term. Basically, we looked at the graph, and I said, okay, if we start at 1, right, when do we get to 5? So 5 is right here. So this is half. We go from 1 to 5 in 0.01 seconds. And then from 5 to 2.5 is another 0.01 seconds. And then from 2.5 down to 1.25 is another 0.01 seconds. So we're seeing that consistently every 0.01 seconds, our concentration drops by half. Right? My son is very angry about something. Poor kid, he's had a rough day. Well, he had a rough day yesterday. Okay, so now that we know the half-life is 0.01, because that's how long it's taking it for it to decay by half. Right? Why is it? Oh, that's not a 5. That's an S. Sorry. That's an S. S's and 5s are really hard to distinguish. S. S's are hard to draw. Yeah, okay. So anyways, now that we know the half-life is 0.01 seconds, we can plug it into this and we can solve for K. So 0.01 seconds. The natural log of 2 is 0.693 over K. So we multiply by K, divide by that. So K is 0.693 divided by 0.01 seconds, or 69.3 s to the negative 1. Right? Or per seconds. Oh, oops. Sorry. 69.3 or s to the negative 1. So this is those cases that the unit is very important. Remember that the unit for a first order reaction, the units of K, is always just time to the negative 1 power. It's always per time. Time to the negative 1 power. Okay? Yeah, Isaac. That's kind of the interesting thing about rates is rates are one of those things that once you get it, they're really easy to see, but it takes a ton of time up front for it to start to make sense because there's all kinds of stuff all over the place. So if you haven't invested some time into learning rates, make sure you do so. So yeah, 69.3. You could maybe argue that you should only really use 1 or 2 sig figs. So maybe just 69 or 70. But yeah. Okay. Then part 3 says, considering the relative concentration of the reactants, briefly explain why the data in the graph are also consistent with the following rate law. I don't love this question. Let me think. Considering the relative concentrations. So in terms of concentrations, we said that one was like 10 times the other. 6.4 times 10 to the negative fourth, 1 times 10 to the negative fifth. So it's like 65 times greater. Skip it, skip it, skip it. No, we can't just skip it. It's a good one. So we know that H to SO3 is way higher. So it's essentially constant. And, oh, okay, there it is. So because it's essentially constant, then we can imagine that its concentration is fine. So it's also consistent with this rate law because the HSO3 is constant. Done. Briefly describe an experiment that could provide evidence to support the rate law given in Part D. Now, this is an easy one, right? What we would do then is we would want to reverse the situation. We would want to keep ozone at a higher concentration and keep it constant, and then use the bisulfite at a lower concentration. Okay. The way... No, you're good, Naya. I'm going to be wrapping up here in a minute or two. This is probably the last one we're going to do. I do want to emphasize this real quick, though. So it says, a solution is prepared in which the initial concentration of the bisulfite is much larger than that of ozone. The concentration of ozone is monitored as it proceeds. So if we wanted to find the bisulfite, we would just swap it, right? So we would want the ozone to be much higher than the bisulfite, and we would monitor the bisulfite. And that's all you have to do is kind of describe. That would be our description there. On Friday, can we go over the experimental procedure? We can go over some experimental procedures. I do want to hit spectroscopy. We do have there. So on Friday, we'll be going over the 2019 exam, which is up on Canvas. So we still have the 2019 exam to do this week. That's our last full free response that I want you guys to do. So that one is up on Canvas, ready to go. I uploaded it this morning. Sorry I didn't get it before this morning. But yeah, that one's uploaded and ready to go. I have it noted which ones you skip. I can pull that up here in a second. Let's make sure that we got this question right. Make sure I didn't miss any details. This was the end of question 1. No. End of question 2. No. End of question 3. Yes. Let's see. Half-life 0.010 seconds. Check. 69. 1 point for the correct value. 1 point for the correct unit. Check, check. So notice, again, it's a K. Whenever you're given a K, they always are going to give you a point for the unit. This is an easy point to get. It's also an easy point to miss, right? So make sure you tack on that unit whenever you have a K. 1 point for the correct explanation. The data considered because it remains essentially constant, right? And so it can be counted into K1. Briefly describe an experiment. Repeat the experiment with different initial concentration of the bisulfite, and then it would be first order. Okay, cool. I'll pull up the Canvas real fast just to show you where it is on Canvas. See, student view. Modules. So it's in modules just like everything else. Right here. 2019 for response questions. Skip problem 1, F, G, and H. Square problem 2, B, G, and H. So just some small parts of the long 1 and 2 problems 1 and 2. Okay, that's probably like 1.5. That's probably 2 short questions. This one shouldn't take you as long because, yeah, you do have those ones that you want to skip. So on Wednesday, I'll develop kind of like a cheat sheet we can maybe go through just so you guys have something to reference. We also can continue to go through these other more free response practice. Let's see, we did this guy. So we still have all these other topics and all these other questions that we can do more practice on. We got practice, practice, practice. We can just keep doing. So that's kind of the name of the game for the next week and a half. AP exam is a week from Thursday. Those are things we've already gone through. Those are questions we've already done, Isaac. That's what it is. Those are problems we've already done. Yeah, so week and a half. AP exams start next Monday, depending on which AP test you have. So this is kind of some pretty significant crunch time. So on Wednesday, I'm going to plan on going through a good reference sheet. And then I'm also going to kind of go through like exam day things, exam day procedures and practices, and maybe walk you guys through the portal on some things. So I'll get some stuff. Wednesday will be a very practical stream. So make sure you can attend Wednesday if you are not planning to do so. And if you don't, make sure you watch the YouTube video of it. But I am done for the day. I am going to wrap up. Lauren, you'll be okay. You'll be okay. One of the biggest signs of intelligence is recognizing that you don't understand something. Okay, it's knowing what you don't know. Right? It's really important. Really important to know what you don't know. I know that I don't know a lot. It's important to know that you don't know what you don't know. You'll be okay, Maggie. You'll be okay. You'll be okay. All right, I am wrapped up for the day. I'll be in Discord this afternoon if you have any questions on anything. If you want more help, if you want more practice, I can work through you guys. I can work through with you guys on anything. So if you want more like individual attention, just drop by in the Discord this afternoon and I can help you guys work through anything. I can share my camera with you. I can walk through problems. We can do all kinds of cool stuff. I feel like you guys aren't really taking advantage of that. So if you need more help, make sure to come by this afternoon. Okay, I guess it's only in like an hour or two. But that is it for today. Have a wonderful Monday. We can have really, so if you've noticed on the answer key, Isaac, almost all of the explanation questions are really only like 1 to 2 sentences. It's really only, if you're using like an entire paragraph to explain something, you're probably wasting time. Most explanation questions on AP exams are like 1 to 2 sentence answers. Yeah, no, it's not an essay. You will not and should not be writing paragraph essays for questions. You can do short, you can do concise. Just make sure you have a complete answer, which is it's tricky for a newer student to do. So, anyways, have a great day, guys. Work on some chemistry. Week and a half. We got this. We can push through. Bye.